Alrighty, let's get started. So we're going to continue talking about optics today. We're going to move on to the next subtopic about it, which is on refraction. But before I do, I want to go ahead and do one or two more examples from polarization, just to make sure we understand how to work those kinds of problems. I did upload the homework polarization assignment to Canvas, so that's posted. I have it due Sunday evening, so there's plenty of time to work on it. But basically, if you remember, with polarization, we would have, let's say, light polarized horizontally. And then we're going to try to go through a series of polarizers. Let's say the first polarizer is at 30 degrees. Then the next one is at 45. And then horizontal again. And so let's say this is our problem. We start with light polarized horizontally. And then we have a series of three polarizers. The light is going to try to make its way through, and I want to know what intensity of light will make it through the system. First thing is, just to make things slightly easier, whenever I give these problems, I just say, assume the initial intensity of the light is I naught. In reality, if you're actually working with real systems, then you'll know the intensity of light is some number. But it doesn't matter what the number is. Let's just say it's I naught, so we just leave it as a variable. And I want to know, if the light starts with this much intensity, what's the intensity that makes it through? And to do it, we use the law of Malus, which says basically the intensity that makes it through, is the initial intensity that started times the square of the cosine of the angle between the light's polarization angle and the polarizer's angle. And if you have multiple polarizers instead of just one, then you just multiply another cosine squared for each polarizer you're trying to make it through. So for this particular example, what we have is we start horizontally and we're going to try to get through this first polarizer. So we start with the initial intensity, and then we're going to make it through a polarizer. So it's cosine squared, and I need the angle. And the rule is the angle is not necessarily whatever the angle of the polarizer is, but rather it's the difference between the light that's trying to get through the polarizer and the polarizer itself. So in this case, light starts horizontally, which means it's 0 degrees. And it's trying to get through a polarizer that's at 30 degrees. So 0 to 30, that's a 30-degree difference. So this angle is 30 degrees. And now the light has made it through. It's past the first polarizer. What that means is whatever made it through is now defined to be polarized at 30 degrees. Because basically what the polarizing filter does is it only lets light through if it's at the right angle. Thus, if the light made it through, it must be at 30 degrees. And so there it is. Light is now past the first guy. He's now at 30 degrees. And now we have to get through the next polarizer. So another cosine squared. This guy's angle is 45, but I'm starting at 30 and I'm trying to get through 45. So 45 minus 30 is a difference of 15. So this angle is 15. Now I've made it through the second polarizer. So whatever made it through, this guy is now at 45 degrees because he made it through the 45-degree filter. Lastly, that light, which is now past the 45-degree filter, tries to get through the last filter, which is horizontal. So I need another cosine squared. And what's his angle going to be? Well, he's currently at 45. He's trying to get through a horizontal, and horizontal just means a 0 degree filter. So 45 to 0 is a difference of 45. And so there we go. My light has now made it all the way through. It started horizontally, it made it through the first, then the second, then the third, and I'm now all the way through. And so to figure out the intensity of the light that makes it through, all I have to do is multiply these terms out. Now, before I do, are there any questions about these numbers? How I got these angles or anything like that?
I have a question. So with the blue ones in between, what is those supposed to be?
Yeah, that's just my way of showing the light. Once it makes it through the first polarizer, I'm trying to make sure you realize that it's not at 0 degrees anymore. It's now at 30 degrees because it made it through the first guy. And then the blue now goes through the 45 degree and makes it through. And so now the light is at 45. It's just a way of showing it visually. Of course, you don't have to show those. You could just say, okay, I've got 3 polarizers. So I have the first one is from 0 to 30, then from 30 to 45, then from 45 to 0. And that's why I get the angles I do. So those blue arrows are nothing more than a visual way of showing that once the light makes it through a filter, its angle has changed. And whatever its angle is, it's whatever the angle of the filter it made it through is. Does that make sense?
Yes, and you said that it doesn't matter if we do add or subtract because by it being cosine is going to still come out positive, right?
Well, not necessarily add or subtract. You're always subtracting. What doesn't matter is if it's a positive number or a negative number. So if you look at the beginning, I went from 0 to 30. And so you could say, well, that's 0 minus 30 is negative 30 degrees. But I wrote it as a positive 30. And so the reason I can do that is just a mathematical thing. You don't have to know why it's true, why you're allowed to do it. You just are. So you're always subtracting the angles. It's just that when you put the angles in these cosines here, always make them the positive number. You don't have to put a negative angle in there. So that's what I was talking about last time. So you're always taking the difference, but if the difference happens to be a negative number, just turn it positive and you're fine. Any other questions before I work out the answer really quick? All right, so if I put this in my calculator, I have cosine squared of 30 times cosine squared of 15 times cosine squared of 45, and I get 0.35 times I naught as my answer. And so what does it mean? It means that whatever the intensity of light starting was, I only get 35% out of the system. So obviously it shaded it. It darkened the light. A lot of the light was lost, but some of it makes it through. This is how much makes it through. So are there any questions about this particular example? All right, let me do one more really quick, just to make sure, because I want to make sure we get all the little kind of various things. Let's say we start with unpolarized light. And so that's the symbol for unpolarized that I use. And I want to get through a few filters. So let's say these two. This guy will be at, let's say 60 degrees. And this guy will be at 45 degrees. And so that's my question here. Now I start with light, unpolarized light. And I want to try to get through these two filters, how much light makes it through. All right, well, we're going to do a similar thing, exactly the same way, except now we have a little bit of a difference because unpolarized light works slightly different than polarized light. We're still using the law of malice. I is I naught cosine squared theta. And so we start with I naught, but now what happens is, because unpolarized light, all it really means is it's random. That basically means that no matter what filter you put in front of it, half of the light will be blocked and half will be getting through. So this first filter, instead of having a cosine squared for him, like I normally would, I don't need it because I know the answer for the first filter. It's automatically a half. Okay, the first example, this first filter here of 30 degrees, I don't know how much gets through, so I had to have a cosine squared for the first filter. But for this example, since I start unpolarized, I know the first filter, the answer is a half for him. So I don't need a cosine squared of 60 or anything like that for that guy. 1/2 is all I need for the first. Now I'm through. So now the light's sitting there past the first filter. He's now at 60 degrees because he made it through. And now that guy is trying to get through a 45-degree filter. Well, this I do need a cosine squared because I'm not unpolarized anymore. I started unpolarized. I went through a filter. The filter took everything away and kept only 60-degree stuff. So now I need a cosine squared for this. And what's the angle? Well, I'm starting at 60, trying to get through 45. 60 minus 45 is 15. So his angle is 15. And now I've made it through the second filter, so I made it through the whole system. So if I work this out, I get the answer, let's see, cosine squared of 15 divided by 2 gives me 0.467. I naught. So any questions about this example?
Can you explain that again, please?
Yeah, so basically it's the exact same as the first example. The only difference is our starting light, instead of it starting at a certain angle, the first one, of course, started at 0 degrees. Sometimes it starts at 90. It could start at any angle. This one happens to start at what's called unpolarized. And unpolarized means that whatever's sending out the light, it sends it out randomly. It's not always in the same direction. And so the rule is, if you have a filter and random polarized light hits the filter, half of all the light is always blocked. The other half can make it through. So, excuse me, the first term, the term that's required for the first filter, instead of having to write down cosine squared of the angle, I don't need to. I know half of the light is blocked. So I automatically put a half there. So no matter what this filter was, if it was a horizontal filter, a vertical filter, 33-degree filter, doesn't matter. That first guy is a half automatically because the initial light was unpolarized. But once you've done that, the rest of the problem is just like every other one. Because now you are polarized. Now you're at 60 because you went through a 60-degree filter. And now you're trying to get through a 45-degree filter. So now we have to do the same thing as before. This next filter needs a cosine squared. His angle is the difference. So it's 60 minus 45 is 15. So if this light initially started horizontally, then we'd work it just like this original problem. Each filter gives us a cosine squared, and we just plug in the angles. But here, the unique thing was the fact that the light started unpolarized. All that means is the very first polarizer, you don't write down cosine squared, you write down a half instead. And then everything else is the same way. Any questions about this? All right, so that's polarization. Any problem I give you is going to be basically like this. Either you start polarized or you start unpolarized, and then there's some set of polarizers that you're trying to get through. You work out the angles, you work out this law of malice thing, and you get an answer. It's a decimal, or you could do it in fractions if you're good with fractions, doesn't matter. And you just work out the answer. The big key is, number one, make sure the angle is the difference in angles. What are you starting with? What are you getting through? And then the other thing is, if you start unpolarized, then the first filter, don't write down cosine squared. Instead, just write down a half and then go from there afterwards. All right, so the next topic of optics, and it looks like it'll probably have to be the last topic just because we're kind of running out of time here, is going to be what's called refraction. Refraction is kind of a phenomenon of light, whereby when light is traveling through, of course, it just travels in a straight line. You shine light, it just keeps on going, except when light tries to go through a different medium. So for instance, you're shining light in the air, no big deal. But if you shine light towards a swimming pool, well, the light is traveling through the air, and then all of a sudden it travels through water. And so what happens is, it turns out that light travels at different speeds depending on what it's going through. If light's traveling through air, then it travels through the speed of light in air. If light is in water, then it travels through a different speed in water. It's slower in water than it is in air. It's harder to make it through the water. If it's in glass, it travels at a different speed in glass. Now, what does that mean? Who cares? Well, imagine this. Imagine you're driving a car. So here's a little top view of a car. And the car is traveling straight upwards like this, okay? So here are your little tires. And you're just driving down the road, and all of a sudden, over here, there's a rain puddle because it was raining earlier, and it's on the side of the road. And so as you're driving, only your right tires hit the water, but your left tires don't. Because like I said, the way the roads are built is there's a little bit of an angle, so the water is moved to the side of the road. So there's only a little bit of water on the right side. Your right tires hit them, but your left tires just stay on the normal road. What happens? Well, if you're not careful, you better be holding onto the steering wheel, because the steering wheel jerks and your car turns automatically to the right. So you have to hold the steering wheel to make sure you keep going straight. If you don't, your car will move to the right. And the question is, why does that happen? Well, the reason is, if you think about it, it makes a lot of sense. As you're driving down the road, water, of course, is more dense. It's thicker than air. So it's harder to move through water. Obviously, if you've ever been swimming, if you try to walk while you're in a swimming pool, you're a lot slower than you walk in the normal air. And so if only the right side of your car, the right tires, hit the water, but your left tires don't, your right tires slow down. And so if the left side of your car moves faster than the right side of your car, then you turn to the right. Because these things are trying to go really quick, but this part can't keep up, and so you just swerve to the right. Well, the same kind of a thing happens with water. I mean, not with water, with light. If you have water here, so down here is some water, and up here is some air, and you shine light towards the swimming pool, the surface of the water, well, you can imagine the same thing happening. Imagine the right side of the light hitting the water before the left side of the light does. Of course, you're thinking like a flashlight beam or something. And so if you have a beam of light, this right side hits the water before the left, and so it kind of curves so that the light then travels in this way. And if you notice, what that means is the light would have kept going straight if the water wasn't there. But because of the presence of the water and the fact that light travels slower in water, the light actually bends. And so now it travels in this new direction, this way instead. This is what's called refraction. It's the bending of light when light goes from one medium to another. So when you shine light at water, it bends. When you shine light at glass, it bends. That's another thing. If you've ever, obviously, if you've ever had let's say a glass of water. So you have some water in your glass and you have a straw. If you've ever seen a straw in a glass of water, it kind of looks weird because it looks like it's broken. It doesn't look straight. It looks like it's in two different pieces. It's the same reason. It's because the light that's coming to your eyes up here only travels through air. But down here, it has to travel through the water, then through the glass, and then to your eyes. And so the light bends slightly instead of moving in a straight line. This is what refraction is. And our job, what we're going to learn, is to predict how the light will bend. How much will it bend? What will be the difference between the angle coming in and the angle going out? And this is obviously quite important in everyday life, not so much nowadays, but certainly in the past. Let's say if you're hunting for fish way back in the past and you use a spear. I know there's a famous scene with Tom Hanks movie where at some point after he's been stuck on the island for a long time, he learns to be able to fish with a spear and throw a spear at a fish and catch it and all of that. At first, you can't do it because where you see the fish in the water is not where the fish actually is, because the light, which is what you see, you don't see the fish, you see the light coming from the fish. The light is bent slightly, so it looks like the fish is in one location when it's actually in the other. And if you don't know, if you're not used to this, then if you try to throw a spear at the fish, you're going to miss. Even though you may throw it exactly where you want it to, the fact is the fish actually wasn't there. It tricked you. And of course, there's other reasons to know about refraction, but how do we do it? Thankfully, it's a very easy equation. It's what's called Snell's Law. Snell's Law. And what Snell's Law says is, let's say we're going from one medium to another, okay? So maybe from air to water. So the first medium we'll call medium 1. The second medium, what the light is going into, is called medium 2. And Snell's Law says that there's something called N, the index of refraction, which I'll talk about that. N1, the index of refraction of the first medium, times the sine of the angle of the light coming in that's going to hit the second medium, must be equal to N2, which is called the index of refraction of the second medium, times sine of theta 2, the angle of the light in the second medium. That's the law. Now, what does it represent? Let's say this is our picture. Here's medium 1. Here's medium 2. Light comes in, hits the surface, and let's say it hits the surface at an angle, this angle here, theta 1. What am I doing? Look at this. This is 2, this is 1, I'm sorry. You start in medium 1 and you're going to medium 2, obviously. So there's light coming in. It happens to come in at an angle, and that angle I call theta 1. How do we measure the angle? The way we usually do it in math or physics or any other science is we make a line, an imaginary line that's perpendicular to the surface. It's called the normal line. Normal line. Where normal, if you remember from physics 1, the normal force, Normal in science means perpendicular. So this dotted line is just a fake line that's perpendicular to the surface of the water or whatever this medium is. And so the light's coming in and we measure the angle with respect to that perpendicular line and we call it θ1. That's the angle coming in. Then it hits the second surface. And if the second surface is different than the first surface, then the light's going to bend. And so if it bends, let's say it bends like this. So now it travels this way. And this angle here is called θ2. And so we can see from the picture that θ1 is bigger than θ2. The angle has changed. The light has bent, and we say it's bent towards the normal in this case, but it can bend the other way too. So that's the picture. That's what you should visualize in your mind when you see Snell's law. The one stuff is where you're starting. The light's coming from that stuff. And the two stuff is what the light is trying to make it into. Now, what about these ends? I didn't talk about n. N is called the index of refraction. Very fancy name. This is basically the number that tells you what medium you're in. Okay, so air has a certain index of refraction. Water is a different index of refraction. Just like all the things we talk about, if we talk about, let's say, thermodynamics, and we're dealing with specific heat, aluminum has a specific heat, water has a specific heat, everything has a different one. Same thing here. The index of refraction is different for different materials. And so this is basically telling you what material is the light in. Now, what does it mean? Okay, it's not just a random number. It actually means something. It's defined mathematically as the speed of light, the normal speed of light in a vacuum, 3 × 10⁸, divided by the speed of light in the medium. Okay, so for instance, we're going to say let air be the same as a vacuum, just to make it easy. So when light travels through air, it travels at the speed of light, 3 × 10⁸. So the index of refraction, n, for air is the speed of light in a vacuum, 3 × 10⁸, divided by the speed of light in the air, which we're going to say is the same, 3 × 10⁸. So it's just 1. Very easy. But what about if we're in water? Okay, so if we're in water, then index of refraction here, H2O. Well, that's 3 × 10⁸, the speed of light in a vacuum, divided by, I'm sorry?
I was just asking, could you scroll up some more?
Yeah, sure. So the index of refraction for water, the way you would calculate it if you wanted to, it's speed of light in a vacuum divided by the speed of light in water. Because like I said, light, when it travels in a different medium, a different material, it travels at a different speed. And in this case, it happens to be something like 2.25 × 10⁸. Anyway, the number, which is more important, is 1.33. The index of refraction for water is 1.33. It turns out the index of refraction for glass, another important one we're going to use, is 1.5. Okay. You don't need to know this. We're not going to use this equation much, if at all. I just want you to know what it means. When you see the index of refraction, it's basically a measure of how fast light travels in that medium. The slower it is, the bigger the index of refraction. Because the biggest it could possibly get, the smallest it could possibly get is 1. Because it can't go any faster than 3 × 10⁸. That's the fastest. So all that can happen is that light can slow down because it's in a thick medium. So you can have 1 if it's in the air, Or if it's in something else, it's going to be something bigger than 1, 1.2, 1.3, 3, anything like that. Now, the types of problems we're going to do, it's probably going to be one of these 3. We're going to be going from air to water or from water to glass, things like this. So these are the numbers we're going to use. And in fact, just like everything, you won't have to memorize these numbers. These will be given on a test if you need to use them. But just get used to the fact that these are the numbers we're going to use for the index of refraction. So with that said, if we were to do an example of how to use Snell's law, this is what we would do. Here's the question. Light is incident on the surface of a pond at an angle of 30 degrees. Calculate the angle of refraction. So this is a typical refraction question. What do I mean by the angle of refraction? All that means is calculate theta 2. What is the angle in the new medium? You started in air in this question. We're incident on the surface of the pond, so we're coming from the air and we hit the pond. So we're going from air to water. And I want to know the angle of refraction. That means what's the angle of the light in the water? Theta 2. So if I were to draw it, here's the drawing. Here's the water. Here's the air. Light's coming in. Here's the normal line. This first angle is 30 degrees. That's the angle it's coming in with. And it'll bend somewhat. And I want to know, what is this theta 2? That's the picture for this question. That's what you should visualize when you read this question. How do we solve it? This is Snell's law. N1 sine theta 1 is N2 sine theta 2. So for our particular problem, the setup is we're starting in the air and we're trying to get through water. So the stuff on the one side is air and the stuff on the two side is water. So N1 is 1. That's the index of refraction for air. And N2, the water, is 1.33. So N1, 1, times sine of theta 1. Theta 1, remember, is the angle of the light in the first medium, which to us is 30 degrees, is equal to, now we're on the two side, so now we're talking about the water, index of refraction of water, 1.33, times sine of theta 2. Well, that's what I'm looking for. What is this theta 2? That's the setup. Any questions on the setup of this equation before I solve it? All right, well, let's do the algebra. I want to solve for theta 2, so I leave that thing alone and I bring the 1.33 over to the other side. So now I have sine of theta 2 equals 1 over 1.33 sine of 30. So how do I solve this though? Notice this isn't theta 2, this is sine of theta 2. I don't want sine of theta 2. What I want is theta 2 itself. And so before I do it, just to remind you of how to do something like this, if you have sine of x is equal to b, let's say, and you want to solve this, for x, you have to get rid of this sign. And just as is always true in algebra, if you want to get rid of something, you have to do the opposite to it. So right now what I'm doing is I'm taking the sine of x, but I don't want to do that. I just want x. So I have to do the inverse of taking the sine, which is take the inverse sine. So I do the inverse sine of x. But because I did it on the left, I also have to do the inverse sine on the right. So inverse sine of b. And what does that do? The inverse sine cancels the sine, and so I'm left with x is arc sine or inverse sine of b. That's what I'm going to do mathematically here. For us, I have sine of theta 2 equals blah, 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 a whole bunch of stuff. Well, I don't want it. I don't want sine of theta 2. I just want theta 2. So I do the inverse sine of both sides. So on the left, I'm left with theta 2 by itself. And on the right, I now have inverse sine of whatever was sitting there. 1 over 1.33 sine of 30. And now at this point, all I have to do is plug this in my calculator. So I do 1 divided by 1.33 times sine of 30. And then I do the inverse sine of that answer, and I get theta 2 is 22.08 degrees. Now I can look to see if this makes sense, if this answer seems to be okay. And here's the rule. The rule is if you're going from one medium to another, and the second medium is more dense, it's thicker, its index of refraction is bigger, then theta 2 will always be a smaller angle because you bent closer to the normal. So if you're going from air to water, your angle should decrease. You're going from air to glass, your answer should decrease because you're always going from a less dense to a more dense medium. And in this case, we started at 30 and I end at 22. It got smaller, so that makes sense. It seems to be okay. Now, on the other hand, let's say we were going from water to air. So maybe you're in a swimming pool with a flashlight and you shine the light to the air outside of the pool. Well, now you're going from water, which is more dense, to air, which is less dense. Now the light will bend in the other direction. So in that case, I would expect my angle to get bigger. Okay, so that's a little rule just to keep in your mind so that when you get this answer, you just check it really quick. Does it make sense? Did it get smaller or bigger? Here, we went from less dense air to more dense water. I expect the angle should get smaller, and indeed it got smaller. So it seems okay. Any questions about this example? All right, well, let me do one more example really quick. Let's say, and I'll just do the drawing instead of writing out all the words. Let's say this is our picture here. This is glass, and this is water. Light's coming in, and light will go out. Let's say light's coming in at 10 degrees. And the question is, what is theta 2? Well, in order to do this, of course, we need to know the index of refraction for glass is 1.5, and for water is 1.33. So there's our question. This is refraction, so I use Snell's law, n1 sine theta 1 is n2 sine theta 2. Really easy. All right, plugging my numbers in. The one stuff I'm starting in glass, so n1 is 1.5. Sine of theta 1 is 10. Is equal to n2, I'm going to water, 1.33. Sine theta 2 is what I want. So just as before, I want to solve this for theta 2. So let me do a little algebra. Sine of theta 2 is 1.5 over 1.33 times sine of 10. And then, of course, I want to get out of the sine, so I do inverse sine of both sides. Theta 2 is inverse sine of 1.5 over 1.33 sine of 10. Now, before I get an answer, I remind myself in my head, in this case, I'm going from more dense to less dense. Glass, of course, is more dense than water. Or another way of remembering is the index of refraction for glass is bigger than water. So I expect my angle to get bigger. So the answer I should be getting should be bigger than 10. Let's see what we get. 1.5 over 1.33 times the sine of 10. Then the inverse sine of that gives me 11.3. So yeah, the angle happened to get bigger. Not that much bigger, but it is bigger. It's different. It's not the same angle, which we expect it should change. So any questions about this? Snell's Law business.
Can you please explain the inverse sign again?
Yeah, so I'll do it a little algebra business here. Let's say we have something like this, 5x equals 10. Okay, just a nice little algebra problem. And I say, I want to find x. Well, I don't have x. I have 5 times x equals 10. But all I want is x. And so, well, we know what to do. We want to get rid of the 5 and leave x by itself. How do I get rid of the 5? I know I divide by 5. And I do it to both sides. The question is, why do I divide by 5? This is something we never think about, but is a deep mathematical issue. Mathematically, the theory going on is that when you had this thing 5 times x, this is an operation. You're doing an operation on x. What is that operation? You're multiplying by 5. But you don't want that. You just want x. So you have to get rid of doing this operation. And it turns out that in math, to get rid of doing an operation, you do the opposite operation. Now for multiplying, the opposite operation is called dividing. So whereas we were multiplying by 5, if we now divide that thing by 5, you cancel out the fact that you multiplied by 5. So they cancel. And so you get x is equal to 2. We're all used to this in algebra. Now, if we go over to this, sine of theta is equal to 0.5. This is exactly the same thing. What I want is theta, but I don't have theta. I'm operating on theta using the sine function, just like I was operating on x using the multiply by 5 function. So I want to do the inverse. I want to do the opposite of taking the sine. And it turns out the name for that is not dividing or something like that. It's called taking the inverse sine. So I do the inverse sine of the operation. But because I did it on the left, I have to do it on the right as well. And just as before, when you do the inverse operation on the operation, they cancel. And so I'm left with theta over here, but now on the right, I have this thing, whatever this thing happens to be. And that I just stick in my calculator and it tells me. I don't know what the number is. Who cares? So you see, these two things are exactly identical. It's just this seems more complicated because it's not the basic multiply and divide, add and subtract thing, but it's the same thing. we're operating on the thing. To get rid of operating, we do the opposite operation. For taking the sign, the opposite is called taking the inverse sign. Just like with multiplying by 5, dividing by 5 is the opposite. Okay, so does that make sense?
Yes, thank you.
Perfect. Any other questions about this particular example? All right, well, that's all I have for today. Next time, we're going to do some more examples, and I'm going to talk about something which is a little bit more high tech that this deals with. Things like what's called fiber optics and things like that, where it's possible, let's say the situation is you're in a swimming pool, so you're down here in water, and over here, so you're in a swimming pool under the water, and you've got a friend out here on the outside of the pool, and you shine light from, let's say, a laser or a flashlight or something under the water. If you don't, well, depending on the angle you use, if the angle's too big, instead of the light coming out so that your friend can see it, the light actually bounces back into the water as if it's a pure mirror. This is what's called total internal reflection. And it happens when you go from a more dense medium to a less dense medium, but only for certain angles. And so we're going to learn what's called the critical angle, which is for a certain situation, what's that angle that makes this water, the surface of the water, act like a mirror. And so this is nice because that's what allows for things like fiber optics. You have a glass cable, okay, glass cable, and you shine a laser light into it, and the laser light, instead of coming out, just keeps on repeatedly reflecting inside the cable until it reaches the end, and then you see the little lights at the end of the little fiber optic glass fibers. And so this is one of the uses nowadays that we use this type of stuff, but this is something that happens in the real world. And so we're going to learn how do we use Snell's law to figure this stuff out. And it's really easy. It's not a new equation. It's the same equation. It's just how to set it up is slightly different. So that's what we'll do next time. So if you don't have any questions, of course, you're free to go. Don't forget about the homework for polarization posted on Canvas. Definitely work on that. And I will see you next time.
Have a good day.
All righty. Thank you.
Have a good day.
Thank you very much. You too.